G'day guys, how you going? So welcome to another video in our video series. Today we're going to be doing a little bit of chemistry, specifically looking at chemical bonding, which is a really important unit because it underpins a lot of the chemistry that you go on. It's kind of like a foundation for chemistry, right? It's really important. So here we go. Some need to knows before we get started. Always remember that positive and negative charges attract together, and this is what we call electrostatic attraction. Remember, opposites attract, and you can see that just on the left here. Also remember that charged particles need to be able to move to conduct electricity. So if these particles, either positive ions, electrons, or negative ions, if they can't move, they can't conduct electricity. Whereas if they can move around, you can conduct electricity. Okay, so bear that in mind as we move forwards. So let's start with a wonderful periodic table, because it's always the best way to start a science video. And I want you to imagine drawing a line from boron, because it's not boring, it's exciting, right? Down to astatine. And if you drew a line from boron down to astatine, to anything to the left of this line is what's called metals, right? Anything to the right of this line is what we call non-metals, all right? And so these are non-metal atoms and these are metal atoms. Now this is really important because it underpins what sort of bonding occurs. So metal atoms to the left of that line, non-metal atoms to the right of that line. Just don't forget to include that cheeky little hydrogen there, okay? It is a non-metal. All right, so here we go. So if we have bonding between metals and metals, so if you're like McRumble Neville, then you're definitely metal. We have metallic bonding, right? If you have a metal atom and a non-metal atom, you have what's called ionic bonding. If you have two non-metal atoms, you have what's called covalent bonding. And these are the three types of bonding that I'm going to try and outline in this video. So here we go, metallic bonding. What's going on? What happens is these metal atoms lose their outer shell electrons, which forms this sea of delocalized electrons, is what we call it. And delocalized because they're not hanging around the same atom. They can go everywhere. So you can see these electrons moving around through that structure. And this is really important in terms of their properties, which we'll come to in a minute. So this is metallic bonding. So let's have a look at what happens to electrons. Well, electrons, the outer shells are lost, all right, forming a sea of delocalized electrons, which you just saw. So what does this mean for conductivity? Well, cast your mind back to the first slide. Can charged particles move? Yes, you saw those electrons moving around. So those electrons can move, therefore they will be good conductors of electricity and heat. All right, well, what about the bonding strength? Again, cast your mind back to that first slide. Were there positive and negative charges attracting together? If there was, then there's good bonding. And indeed, there is. Lots of positive metal ions and negative electrons were in the bonding, which means they're going to attract. So metallic bonding is strong. What does this mean? It means they generally have really high, I should say, melting points and boiling points, and they are solids at room temperature. So most metals that you think of will be solids at room temperature with high melting and boiling points. What other properties do metals have? They're quite useful. You can hammer them into shapes to make, knives or a hammer, and this is a property we call malleable because those metal atoms can sort of slide over each other as we hit them with a hard object. We can shape them into different shapes, which is really useful. This is called malleable. Can be hammered into shapes. Ductile is another property of metals. We can stretch them out into wires, which is really useful in headphones and electrical appliances and things like that. Okay? All right, so let's have a look at ionic bonding. So between ionic bonding, you have a metal atom and a non-metal atom. What happens is the metal atom will actually transfer an electron or give an electron to the non-metal atom, which means the metal has lost an electron. And if a metal atom loses an electron, remember that electrons are negatively charged. What's going to happen is it will become positive. And the non-metal atom which gains an electron, which is negatively charged, will become more negative, okay? And so they form what are called ions. And if you get positive and negative, they're going to attract and they're going to stick together. Just as a note, an ion is a charged particle. What this means is it either has more protons than electrons and therefore would be positively charged, or it has more electrons than protons and would therefore be negatively charged. And that is what an ion is, a charged particle. Now, there's not going to just be two ions hanging around, there's going to be billions of them. And so what happens in ionic bonding is they form these structures here where more and more ions, positive and negative, come in and they form this regular pattern which we call a lattice. And you can see each positive metal ion is completely surrounded on all four sides by negative non-metal ions. And each negative non-metal ion is surrounded on all four sides by these positive metal ions, right? And so this lattice structure where each positive is completely surrounded by negative and each negative is completely surrounded by positive is incredibly strong, incredibly strong. That bonding is really, really strong, which underpins a lot of what happens in ionic bonding. And that is a lattice structure just there, okay? So let's think about ionic bonding. What happens to electrons? Well, they were transferred. So there's a transfer of electrons from the metal to the non-metal atoms. Cool? Conductivity. All right, in that lattice structure, all those positive and negative ions are stuck together. They're locked in that structure. They can't move. And if they can't move, they can't conduct, okay? So as solids, the ions are trapped in a lattice. Therefore, they cannot move. Therefore, they cannot conduct electricity. However, if I took this ionic substance and I dissolved it in water, for example, and so that lattice structure broke apart and those positive and negative ions could whiz around, then they could conduct electricity. So as solids, ionic substances do not conduct electricity, whereas if you dissolve them in water, they will conduct electricity. All right, bonding strength. Remember, those positive and negative, that is incredibly strong. There are lots of positive metal ions and negative non-metal ions strongly attracted together in that lattice structure, which means you have incredibly strong bonding. And what this means is they will be solids at room temperature and they have really, really high melting and boiling points, higher than metals, right? Much higher than metallic bonding because of this incredibly strong bonding. The only other property that we really need to think about for ionic substances is that they're really brittle, right? If you hit them with a hammer, they can be smashed into pieces. If you hit them hard enough, that is, you can actually break them into smaller chunks. And this is what we call being brittle. They're not malleable or ductile. They are brittle, okay? All right, so here we go. Covalent bonding, lucky last. So in covalent bonding, we have these two fluorine atoms. And what I have done is I have put just their outer shell electrons. And you can see that each of these fluorine atoms has 1, 2, 3, 4, 5, 6, 7 electrons in their outer shell. Now remember the octet rule, as we say it, means that they need 8 electrons in their outer shell to be stable. But each of these only has 7. So they're unstable. They're not happy, right? So what do they do? Well, what they are going to do in covalent bonding is they're going to come together and they are going to share 1 electron each, right? And so in this case, let's look at this fluorine on the right here. There is 1, 2, 3, 4, 5, 6, 7, 8. There are now 8 electrons in its outer shell. So it will therefore be nice and stable. And let's look at this fluorine on the left. 1, 2, 3, 4, 5, 6, 7, 8. There are now 8 electrons in the outer shell of this fluorine, and therefore it will be stable, okay? And so covalent bonding is where these electrons are shared between 2 non-metal atoms, all right? So here we go. So what happens in electrons? We literally just went through it. Electrons are shared between non-metal atoms. Well, what about conductivity? Well, they are really poor conductors. Look back there. All those electrons are locked up in that atom structure. They're not free to move around. You don't have moving charge particles, and therefore they are really poor conductors of electricity. What about the bonding strength? And this is where it gets a little bit more complicated for covalent structures. Between those atoms, between those fluorines where they're sharing those electrons, that bonding is really strong. It's holding those fluorines together really tightly, okay? However, because there are no positive, that fluorine F2 we now have, no positive or negative charge overall, it means that this fluorine is not attracted to other fluorines around it. And what that means is there is not a lot of attraction between molecules, which means that their melting points and boiling points are really quite low. They are typically gases at room temperature. So you think of covalent substances, oxygen, nitrogen, hydrogen, really common ones that you will have heard of, and they're gases at room temperature. We actually breathe them in. So because there is not a lot of attraction between molecules, they have low melting and boiling points. All right. Lucky last, and this will be covered in another video. Covalent substances can form these giant structures, and these giant structures are called things like diamond and graphite, are really quite useful because they have some unique properties which we will cover later, but it is beyond the scope of this video. And so this is me trying to break down those 3 bonding types in as simple as possible in terms of the things you need to be able to do. I really hope this helps, guys, and I'll catch you later.